So hello friends, I'm going to show you the analysis of elastic plastic collapse of a thin wall elbow under implant bending. So this problem comes under non-linear static conditions, and it involves buckling or collapse behavior where the load displacement response shows a negative spin, and in this case structure must release strain energy. And this problem can be treated dynamically also by Riks algorithm. So I'm going to use the Riks algorithm method, and it is generally used to predict unstable geometrically nonlinear collapse of a structure. It can include nonlinear material and boundary conditions too. So this method is used for also for cases where the loading is proportional. So I'm going to create parts. I already created all the parts and steps, but I will go through it and make you understand also. So this is the part. So modeling space is 3D and type is deformable, and created a shell shape. Those for shell shape I have to define a path. So here the path sketch. So here the path sketch, elbow region, leg regions. These leg regions, all the dimensions are given in a box tutorial, so you can see it. And then section sketch. So here the section sketch, you can see the radius dimension 7.805. Okay, and then material model. In the material model I have defined the elastic material, and so in mechanical elasticity and elastic M's model is defined, and also Poisson ratio. And then in mechanical plasticity and in the plastic, then you have to define yield stress and plastic strength. So I have already defined all these things. So here the material model, and then you have to define sections. For elbow region I have defined one section, and for leg region I define another section. So for elbow region, the shell thickness value is 0.41 and material is 5, same for both legs and pipe. And thickness integration point I have kept 7. So for elbow region, and this is for leg region. So tail thickness in this case is 0.37 inch, and material is same as earlier, and thickness integration point 7, and all rest of the options keep default. Then you have to create the instance. I have created already in assembly module. So here the instance, that is 5, and then define this define the step, that is static Riks method. Here's the, and there should be non-linear geometry, so it is on. And there are two criteria for stopping, that is stopping criteria: maximum load proportionality factor and maximum displacement. Either maximum load proportionality factor and maximum displacement can be used. So I have defined maximum load proportionality factor. So what is that maximum load proportionality? What is maximum load proportional factor? So I will give explanation what is that. So the loading during the Riks step is always proportional, and the current load magnitude is defined by total is equals to P naught into lambda into P reference minus P naught. P naught is the dead load, P reference is the referent load vector, and lambda is the load proportional factor. You can get this theory in the paper or so in a Bacchus tutorial. So lambda is the load proportionality factor. I've given the explanation now. Okay, we'll go to the step. So maximum load proportional factor are defined 2, and then maximum number of incrementations 100, and arc length. And instead of time in static general, here you have to define the arc length. So estimated total arc length is 1, and the arc length increment 0.05 to maximum 0.5. Okay, rest of the option keep default, no need to define anything. Okay, then field output request, update all the stress, strain, displacement, velocity, forces, reactions. Okay, and then for whole model, and then how requested history output, all kind of energy are requested. And then you need to define boundary conditions. So I have created boundary condition, 3 boundary conditions. So we'll go to the boundary condition in the load, and then I'll show you, but I'll not go. Okay, So first boundary condition is the x symmetry. This is the x symmetry along this edge. You can see the red edges. Okay, x symmetry, that is u1, ur2 and ur3 is equal to 0, and I have created another datum system paralleling the default datum system. So I have picked that from that reason viewports. So the another datum system, so it should match the analysis as per the abacus as per given by the abacus tutorial. So it is now that this datum system is according to the abacus tutorial. So here is the first boundary condition. Now we will go to the second boundary condition, and the second boundary condition is the that is long straight pipe fixed end. This is the fixed end, and fixed end of this leg. Okay, so I have defined encaste, and again I have picked the another datum system that is defined by me. Okay, and we'll go to the next boundary condition. That is, but first of all, to give that boundary condition we need to define a reference point. So I have defined a reference point here. So you can see first you need to create a datum point, and then you have to define the reference point here at this point. Okay, I already created that, and then you have to give boundary condition. That is in step 1, the earlier two boundary condition was defined in initial step, and this boundary condition is defined in the step 1. So in this ur1 is g minus 0.2 radians, and I have picked again I have picked another datum system that is defined by me. So this is all about loading condition, that more load and boundary conditions. Now we'll go to the mesh region, and then you have to controls. Okay, I have to set controls. So I have defined the technique as a sweep, and I have used quadratic dominated element shape. Okay, and then element type, and the element type will use a standard, and family is a shell, and geometric order is quadratic with the degree of freedom is 5, and rest of the options keep the default, and the element use SZR5 and 8 node double curved thin shell reduce integration, and using 5 degrees of freedom per node. That's it. It's all about meshing, and then mesh it from this mesh part. Okay, I already generated the mesh. Then go to the job model and create a job. Okay, job 2 I have already created and completed that analysis. So I will show you directly the results. Okay, results. So I'll go to the first stresses. So 1 second. This is the collapsing of a thin walled elbow under in plane bending, and you can see the stress is generated. I'll show you displacement. This is the displacement while collapsing, and then UR rotations. You can see the, and then RM moment is the moment. You can see the moment magnitude. All the dimensions were in inch. Now I'll show the plots. I've already created some plots. So we need to create a XY data first of all. So I'll create it, but I'll show you the procedure. So already field output, and then you select the unique nodal. Okay, then you will get the options, and then select whatever you want. I have selected I have pick the node from the node sets, that is M set9, that is the reference point. It is the reference point that I've been selected. Okay, now the reaction moment, stress component, use spatial UR, and save, then save. Okay, already created, so I will cancel it, and then operate on XY data to create the graphs. I already already plotted, so I'll show you the graphs. This is the moment and rotation. This is the plot for moment and rotation. You can see the moment increases and then suddenly decreases. And I'll show another graph, that is load proportionality factor. This is load proportionality factor. It is not going beyond the 2, just it crossed the limit of load proportional factor 2. So at that point, at means that percentage of load, it gets it gets converts, and now you can see the arc length is beyond 1. We have set arc length as 1, but it goes behind 1.5. This is the percentage of, that is load proportional factor, means it is the percentage of the load application. So here it goes behind 2%. So this is all about the elastic plastic collapse of a thin walled elbow under in blend and blending. You can see the again, you can see the plot or action and stresses, all these things. I'll show you the strain energy also. This is strain energy curve along arc length. So this is the energy. You can see the, as I have mentioned that this kind of structure must release energy. So here is the stress energy, strain energy released as and this is the plot of energy and arc versus arc length. So thank you for watching. I'll come with next problem soon. I hope so you like this video. Thank you for watching it again.